Good evening, everyone. I am Bandhuka Kuruppu, Technical Events Coordinator for Civil Engineering Sectional Committee. So this today is our fourth session of this lecture series on structural designs of highway bridges. And I think Professor is just after a session at university. So, sir, our sincere gratitude for your commitment in conducting this lecture series to uplift the knowledge of practicing engineers. Thank you very much, sir. And last week also I mentioned that we have created a WhatsApp group for sharing related study materials and video recordings of this lecture. So today also I will share the link in the chat box. And over to you, sir.
Thank you, Vanika. So last time we talked a lot about concrete technology related things and why reinforced concrete is not as good as pre-stressed concrete. And then we talked about what has happened historically, and then how to get rid of some of the materials in the bridge and go for beam slab type bridges rather than complete slab type bridges. And then we have talked about the kind of reinforcement that you need, and what is the type of situations that you can handle when you want to go for foundations rather than going for deep foundations with piles. How you can make use of the large foundations by using cement mixed with ABC. So those are the things we covered. And Manu, can you tell me whether I explained how to do the I think I have already explained how we can make a mixed design. I explained it in great detail earlier.
Yes, sir. To a certain extent, it was explained.
Yeah. So today, what I do is I'll go little deeper into the Euro code and explain the design method of the Euro. Okay, right? So I will explain the design method of the Euro code. And last time I explained that we can, when you want to find the strength of concrete, we can either use the cube strength. On the other hand, we can use cylinder strength. Then I explained what is meant by 0.45 times FCU, but I have not gone very much deep into it. So today, what I do is, assuming that you are capable of designing a beam, I will actually go into the details of Euro code. And so now I'm going to share the screens and also share the white screen with you. Right. So right. So now you can see the white screen. Is that right?
Screen is not
the
visible,
white color one. White color one.
The papers are can be seen.
Paper.
Yeah.
Right. So let's see the fundamentals of. So what is the difference between cube based testing and the cylinder? And this civil engineering sectional committee on 13/3/2023, page number 1. Right. Okay. So let's see. I told you that when we test a cube, we are going to get a strength, and actual strength is 0.8 times FCU. And then I explained that we consider that we are testing for in compression, and we are using it in flexion. So to relate these two, we multiply it by 0.85 because we are testing in compression, but we are using in flexion. So a 0.85 factor has been introduced. 0.8 times 0.85 is 0.68. So we say the strength of concrete is 0.67 divided by 1.5 times FCU. So when you are dealing with the cube. So what happens when you are dealing with the cylinder? When you are dealing with the cylinder, we don't have this effect of thick plates of the concrete testing machine. We don't have the effects of this thick concrete testing machine. Right? The reason is cylinder is tall, so this effect is negligible because these areas can have this stress without any restriction, and it can be what we get is the actual strength. Then, and we call this FCK. So, what is the flexural strength? Flexural strength in compression. Flexural strength is compression is 0.85 times FCK. Flexural strength in compression is 0.85 times FCK. It's the same relationship that we use for cubes. We use it for cylinders as well. We use it for cylinders as well. Right. Then we have to get the characteristic strength. That means we have to divide this by 1.5, which is a factor of safety. And I'm using the Eurocode notation. There's something wrong. You are viewing Mohammed Nizam's screen. What is that? Why is that? There's something wrong with the Zoom. You are seeing the full screen now, I hope. We are seeing somebody else's screen.
Yes, that's happening. Yeah, someone is sharing his screen.
Mohammed Nisam's screen.
Yeah, we will
disable now. It's okay. Now it's okay.
Yeah.
Okay. Right. So when you get 0.85 divided by 1.5.
.567, sir.
Yeah, 0.85 divided by 1.5. You get 0.567. Right. FCK. So earlier we got 0.45 FCU. Now we are getting 0.567. Right. So let's see how we can deal with Eurocode. Right. How we can deal with Eurocode. So now we have a cube. We have a cylinder that we have tested, and we found that the strength is FCK. And if you look at Eurocode, it says C2530. Then it says C3037. There are various strengths, and 30 means cylinder, 37 means cube. So we have to see how we can make use of this to determine the reinforcement in a beam or a slab when it is subjected to a load, and we want to determine the reinforcement quantity. So what is the theory behind it? So for that, first we have to look at the stress strain curve. And the concrete stress strain curve goes like this, and its final strain is 0.0035, and we say that it is reached at a stress of 0.567 FCK. Because that is the maximum stress we can allow in concrete. And so that is the situation with concrete. This is the situation with concrete. Then we have to look at steel. Go straight, then it tries to deviate, and we get 0.2% proof stress. And we come this way, and if we say y divided by 1.15. So you get the strength of steel divided by 1.15. So you get 0.87 times the strength of steel. So on one side we have a stress strain curve for steel, and the other side we have a stress strain curve for concrete. Now this is page number 2. Now we look at now we know what is the elastic modulus of steel, 200 kilonewtons per millimeter squared, and we are using 500 megapascal steel, and 500 multiplied by 0.87 . 500 multiplied by 0.87, we get 435. And then we have to find the corresponding strain. And that is sigma is equal to E times epsilon. And what we want is epsilon, and that is sigma divided by E. That is 435 divided by 200 into 10 to the power 3. So we get 435 divided by 200. So you get epsilon is 0.00217. Right. Now we know what is the strain at which concrete yields, steel yields, and the strain at which concrete crushes. So this is the strain at which steel yields, and 0.0035 is the strain at which concrete crushes. So now we can draw a stress strain curve. So before doing that, I would like you to appreciate the difference between steel and concrete. Steel and concrete. So in steel, if you have an I section, we say, the beam, then we can say the stress diagram is like that, and M over I is equal to sigma over I. This is a Benny formula that we all know, and for this to be valid, plane sections should remain plane and elastic. It should be elastic behavior, not plastic behavior. Within the elastic range, MOI is equal to sigma OI is applicable. So, but concrete behaves differently. Concrete behaves as a cracked material below the neutral axis. Concrete behaves as a cracked material below the neutral axis, but still we assume plane sections remain plane, so the strain diagram will be like this. Still we assume plane sections will remain plane, and because of that reason, the strain diagram will be like this. So we have to first appreciate that this particular behavior, that is below the neutral axis, concrete is cracked, and so if you get a section behaving as an elastic material, this is the stress diagram. So this is the stress in steel, this is the stress in concrete. But if you look at the strain diagram, it will be like this. Can you understand it? So what we do is, now let's look at a very special situation, and that is, we have a concrete section that is going to crush at 0.0035, and at the same time the strain in steel has just reached this limiting value of 0.00217, and this is the depth to the steel reinforcement, and this is x is the depth to the neutral axis. So the section looks like this, and here you get at this level some reinforcement, and all this area is in compression, and below cracked. So let's see, this whole depth dimension is d. Up to this point from the top 5 is d. Then this is d minus x. Then you can say 0.0035 divided by x is equal to 0.00217 divided by d minus x, and from this we can say 0.0035 d is equal to 0.0035 x plus 0.00217 x, and x over d ratio is 0.0035 divided by 0.0035 plus 0.00217. So you get a value like this. Right. So then what you get is x over d, and we can actually calculate the x over d ratio with this, and that is 0.0035 divided by 0.0035 plus 0.00217, and the answer is x over d is equal to 0.617. Then now we have to ask the question, is this acceptable? Is it acceptable to have concrete crushing as soon as steel reaches yield point? Answer is no. Why? Because we like to get a warning. If you want to get a warning before failure, what we need? We need steel yielding before concrete crushes. We like to see steel yielding before concrete crushes. So what is that condition? To fulfill this condition, this code says, now we can't go for this type of situation. The maximum we can allow for x is this, and x over x is maximum value of x is 0.45 d. So we can't go up to 0.617, and it says this, and then what happens? The strain in steel becomes very high, which means the steel yields, and when the steel yields, what happens to the concrete? We are in somewhere here, steel is yielding, so what will happen to the concrete? Concrete will start cracking, and cracking in concrete means it's going to fail. So we panic, and we don't use the bridge. So that is the situation we like to have. So what we do is, so we like to see that x over d, maximum is 0.45 or x maximum is 0.45 times d. Now let's see how to make use of this. It's number 4. Now let's see what will happen if we are going to have a moment which is large enough for x to be 0.45 times d. So we have a moment which is large enough for x to be 0.45 times d. The breadth of the section is b, and we are going to have some steel, the adequate amount of steel at a depth d. And let's derive an equation for the maximum moment carrying capacity. Let's derive an equation for the maximum moment carrying capacity without using any compression reinforcement. That is as singly reinforced. So this beam is singly reinforced, and as you can see, it has only one set of main reinforcement that is close to the bottom, and we don't have any special bars in the compression zone. We don't have any special bars in the compression zone. So what happens now? So what happens now is, we know bending moment is equal to force times lever arm. And if you look at this section, again we have to see how we can find this force. And to find the force, we have to see under which situation we are in. So we have the neutral axis at 0.45 d. So what happens when you are loading a section? Initially, it will be like this, a triangular stress. That means, if you look at the stress strain curve for concrete, we are somewhere here. Now, that is number 1. We are somewhere there. Now, we can keep on applying the load. It might be like this. That means we are somewhere there too. And we keep on loading, then it will become something like this. It's number 3. And we say we are somewhere there close to failure. And we call it ultimate moment carrying capacity of a section. So we know now, when you try to deal with the rectangular parabolic situation, it takes a lot of time, very difficult to do the calculations. So we are given an equivalent stress block, and that has a magnitude of 0.567 FCK, and depth to the this depth is S, and S is equal to 0.8 times X. Is that clear? Then now we can find the lever arm, that is from the center point to the reinforcement, and that is D minus S by 2, and that is the lever arm, we said, is D minus S by 2, and S is 0.8 times X. X is equal to 0.45 times D. So we are considering a very special case where the beam is carrying its maximum moment, and we want to see what is the maximum moment. So when the beam is carrying its maximum moment, the maximum depth of concrete section will occur, and the maximum depth of concrete section is 0.45 times d. So this is the situation. So now you can write an equation for the bending moment. The maximum bending moment is equal to force. So what is the force? Force is stress 0.567 times FCK times multiplied by the breadth of the section and the depth of the section. And depth of the section is S, and S is 0.8 times X, 0.8 times X, and X is 0.45 D. So that is the force multiplied by lever arm. Lever arm is D minus S, that is half. S means 0.8 times X, and X means 0.45 times D. So we get an equation like that, and if you multiply all these numbers, you have to multiply. First, we can find what is this lever arm, and we are talking about the minimum lever arm, and the lever arm is 1 minus 0.5 times 0.8 multiplied by 0.45. So you get 0.82 Z. So Z minimum is 0.82 times Z times D. What is Z maximum? There's a maximum value given, that is 0.95 times. What it says is, you can't have a very thin section under compression. It has to be of substantial thickness. And to get that, the Z maximum value is limited to 0.95 times D. Is that clear? Now we can sort out this equation. Bending moment is equal to force. Force is 0.567 multiplied by 0.8 multiplied by 0.45 multiplied by 0.82, that is 0.282 times D, and you get 0.167 FCK B D square. So that is the maximum value of bending moment that this can carry as singly reinforced. So can you understand how I got it? I have considered a very special case. The special case is the steel has already yielded, and there's a huge force taken by concrete, and that is the maximum force we can allow, because there are limitations. The one limitation is, you cannot go below 0.45 times D for the stress block. And then when you consider the equivalent stress block, you have to again consider additional conditions, right? So we are then using all this special case where everything is stress maximum. We have derived a formula, and that formula gives the maximum bending moment carrying capacity of a concrete section without using any compression steel. Only the steel. We use steel, but it's only for tension, no compression steel. The whole compression is taken by concrete, and that's the concrete is a very good material for carrying compression. So we don't have any problem with that. Is that clear? This equation is very, very important, and because bending moment is given by 0.167 times FCK multiplied by BD squared, and if you are familiar with BS 8110, you would find another equation which says bending moment is equal to 0.156 FCU BD squared. So it's also very similar equation. Any questions up to now? If you want, you can ask. If you have any questions, please ask. And I think you can include it in the chat box as well. So join here, right? So we don't have any messages of significant nature in the chat, and so I will continue. Right. Okay. So basically, this is the situation. Now let's look at little more theory, and that is how to find the reinforcement. Now to find the reinforcement, we have used various methods, but we are going to find the reinforcement by using fundamentals. So we have a beam, and we know it has a depth to the neutral axis x, and there's only some area in compression, and that is called S, and S is equal to 0.8 times x, and we are going to have some reinforcement here, satisfying the cover requirements for durability, and we know the section, we know the breadth of the section, we know the cover requirements, so that means we know the depth, D value, depth to the middle of the reinforcement. D is also known. If you know the cover required, say 45 millimeters or 40 millimeters or 50 millimeters, immediately you can decide the D value, provided the overall depth H is known. So H is something, again you select something like 600 millimeters. So whatever the value that you select, right? H is the value that you select. Breadth is the value something like 300 millimeters. Again you select it. And then somebody has said, it is supporting a continuous beam subjected to a bending moment of 70 kilonewtons per meter. I'm just taking one example just to give you some numerical values. And let's say the bending moment is, let's say the span is 6 meters. And so you can get 6. So you might get a bending moment of about 232, 240 kilonewton meters here, and a bending moment of about 200 to 240 might appear over the support. So let's concentrate on this section, assuming that the bending moment is going to be something like 240 kilonewton meters. Now we have a situation, and how we are going to deal with it. So that is the rule. There is a situation 240 kilonewton meters, and we want to see how much reinforcement is needed to resist 240 kilonewton meters by 600 by 300 section out of FCK equals 30 megapascal. That means we are going to use 30 megapascal concrete for this 600 by 300 section, and we have to find the amount of reinforcement needed to carry a bending moment of 240 kilonewton meters. Now, how do we solve this problem? So we can write two equations. The first one is bending moment is equal to force in steel multiplied by lever arm. So what is the force in steel? 0.87 times F5 times area of steel. And lever arm is Z. And what is the Z value? Z is equal to D minus S by 2. So that is 0.87 times Fy is, and that will be D minus S by 2. If you look at this diagram, you can see Z is distance to the center of this from here. So that is D minus S by 2, because this particular distance is S by 2. We have a rectangular stress block. So the center of the stress is at the center of this stress block. So the lever arm is the distance between steel and centroid of concrete. That is the lever arm, because in the upper part, the force, compressive force is carried by concrete. And here in the lower part, steel carries the tension. So we have a tensile force, compressive force. They are acting at a distance, so they can resist a moment. So that is the theory. So we get this number 6, and then now we have a problem. Now, how do you find Z? How do you find Z? Now that is the big question. And to find Z, I'll show you. We can do a small calculation, and I will show you that. I will share the screen now. Can you see the screen? Yes, you can see the screen. And so when we have to deal with this situation, we have to think about the various concrete properties. And here you can see 20 FCK 25, FCU 30, 30 37, 35 45, 40 50, 45 55, 50 60. So those are the cylinder strength and cube strengths. And then you get various other parameters like tensile strength of concrete, the elastic modulus of concrete, and so on. And here you get the elastic modulus of concrete. Then from this, you can cite the lifespan of a structure, and depending on the way you are going to cast it, you can come up with a particular class requirement, and then from this chart you can decide how much cover is needed. So for bridges, generally we go for about 40 millimeter cover, because bridges are outside and we like to have a reasonable cover. So some typical value is 40 millimeters when it is outside surface. So that's a value that is often used in Sri Lanka. But if you want to allow for some construction tolerances, you can go up to 45 or 50 millimeter cover. You can go up to about 45 or 50 millimeter cover. So we'll come to that. So we'll come to that later when we want to get the real cover for an actual situation. So we'll come back to this later. But so this is the theory that I've been explaining, and you can see S is equal to 0.8 times X, and you can also see 0.00335 and the maximum strain here, and 0.567 FCK also can be seen. So now we have a situation where we like to know the moment carrying capacity, but what we like to know is Z value. What we like to know is Z value, and so basically we have a situation where we have concrete in compression, steel in tension, and we have a neutral axis at a depth of X, and so we have a force FCC, and we have a force FST. So, and if you look at the stress diagram, comes like this, and it is 0.567 FCK. So basically, I will stop share for a moment, and you can see the situation where we have a section like this, and part is in compression. These are in tension, and then this is the FCC, that is the force in concrete, and this is FST, that is the force in steel. That is the force in steel, right? So that's the situation. And so if you want to look at the equilibrium, we can say the lever arm is Z, the bending moment M is equal to FCC times Z or FST times Z. So now we look at I'll share the screen again. And here you can see FCC is equal to 0.567 FCK multiplied by the breadth of the section multiplied by S and then Z is equal to D minus S by 2 and S is equal to twice D minus Z. Twice D minus Z. And so we can say FCC is equal to 0.567 multiplied by 2 1.134 FCK multiplied by B multiplied by D minus Z. And then we can say M is equal to FCC times Z, that is 1.134 FCK B D minus Z multiplied by Z, and then we can say M is equal to FCK M divided by FCK B D square is equal to 1.134 FCK BD, and here we have taken BD squared, so you get 1 minus Z over D and Z over D and Z over D. So you get Z over D squared minus Z over D plus, and we call this parameter K. So you get K divided by 1.134 is equal to 0. And this is the second order equation of Z over D. So we can find the solution straight away. We can find the solution straight away. Is that clear? Just one moment. I'll stop sharing. Right. So what you get is bending moment M is equal to FCC times Z or FST times Z. And then we found that FCC is 1.134 times FCK B D minus Z. And then the moment is 1.134 times FCK B D minus Z times Z. And we substitute a value called K for M over FCK BD squared. And that is equal to 1.134 FCK 1 minus Z over D times Z over D, because I have divided this by D squared. Both sides I have divided by D squared. So then we can get a second order equation like this. And this is page number 7. So what we can do is we can find the solution for this, and X is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. So here you get minus b, sorry. So then z over d is equal to minus b, and that is 1 plus or minus square root of b squared. So that is 1 squared minus 4, and a is 1, t is k over 1.134. So you get divided by 2. Divided by 2. So you can write this equation as 0.5 plus. So I'll write the equation, and you can see it's given in the note as well. And let's see the value. I'll share the screen again, and here you can see Z is equal to D. Z over D is equal to 0.5 plus 0.25 minus. Here you get 4k over 1.134. So because we have a 2 here, so when you divide it by 2, because here you get 0.25 minus k over 134. So the equation is, you get Z over D equals 0.5 plus square root of 0.25 minus k over 1.13. And if I stop sharing, you can see the equation. It's here. So you can get this equation. And once we have this equation, we can straight away find the Z value. So we can share the screen again. So we can straight away find the Z value. And then we can find the reinforcement as well. So we'll look at an example now, just to give you some idea. And we'll go for the example that we earlier looked at, and that is 600 millimeter deep beam and 300 millimeters wide, 30 megapascal, and let's say 45 millimeters of power, and so you can see, we look at the early example: 600 millimeter beam, 300 millimeters wide, 30 megapascal concrete, and we are going to get some reinforcement, and here you are going to get some reinforcement and some nominal bars there. Now the most important thing is to find what is this depth and what is Z. Now to find Z, we have a equation, but there you can get this K factor. So the bending moment is 240 kilonewton meters. So the bending moment is also known. So what you do is, first you find K is equal to M over FCK BD squared. For this, you have to find that D is equal to 600 minus 45 minus 10 millimeter links minus, let's say we are going to use 20 millimeter bars, 20 divided by 2, 600 minus 45 minus 10, 545. So you find D is equal to 535 millimeters. D is equal to 535 millimeters. So this will become 240 into 10 to the power 6 divided by FCK 30 multiplied by 300 multiplied by 535 squared. So you get K as 240 divided by 30 divided by 300 500. 0.093 less than 0.167. So that means this section can be singly reinforced. We don't need any compression reinforcement. Then we can go for this equation. Z over D is equal to 0.5 plus square root of 0.25 minus K over 1.134. So it is equal to 0.5 times plus square root of 0.25 minus 0.093 divided by 1.134. Z is equal to so the answer is 0.25 minus 0.0093 divided by 1.134. 0.25 minus then not 93 divided by 1.134 equals square root answer plus 0.5. So that set as 0.909 D, or if you look at the value, that is 535 into 0.909, and that is 486 millimeters. 486 millimeters, and then we know Z. Now we can find the reinforcement. The reinforcement is equal to M is equal to 0.87 F5 SC AS multiplied by Z, and M is 240 into 10 to the power 6 is equal to 0.87 into 500 into AS multiplied by 486 millimeters, and then from this you can find the area of steel. AS is equal to 240 to the power 6 divided by 0.87 divided by 500 divided by 486. So you get 1135 millimeters squared. So you can use two numbers of 25 plus one number of 20. So you get 490 into 2 plus 314, and that is 490 into 2 plus 314. So you get 1294 millimeters square. So you can do the detailing of the beam like this, and here you need 25 bars, H25, and that is H20, and the area is 1294, and the cover is 45, and you get a power of 10, then you get 20 and or 25, and the width is 300 and 30 megapascal. So that is the simple method that can be used for calculating the reinforcement in case of a beam or even a slab using the Euro code. So I just did it. It's a simple calculation, not a difficult one, but I did it fully just for the completion of the lecture. So that means if you know the bending moment, we have no problem. Now let's see. Let's come back to our reinforced concrete design of the bridge, and we are talking about something like beams at a spacing, and its loaded with panels, and we are going to fill this with concrete, giving a thickness of 200 millimeters, and these can be about 300 to 350, and height can be about 400 to 600. And we are going to make the bridge by recasting these panels containing some reinforcement. Now you have to see what is the reinforcement needed in the beam. What is the reinforcement needed in the beam? And what is the reinforcement needed in the... So which means the theory we have just covered can be used, provided that you can find the bending moment. Provided that you can find the bending. So that is the design method, and then it boils down to a simple question: how are you going to find the moment? How are you going to find the moment? Is that clear? So basically, this is the simple optimized bridge, and we wanted to know how to get the reinforcement calculated, and you can see we are going to cast it in several stages. So we have to understand the loading sequence. So what is the first stage? We cast the concrete beam on ground. Which may be about 6 to 8 meters or even longer. We can go up to about 12 meters. And then what we do is we lift it up, place it on the supports. Supports are abutments and piers. And if you like, you can give a prop as well at 2 points. Sometimes giving a prop is not that feasible. Generally, when you are giving a prop, we give the prop at 1/3 point. If you are giving a prop, we give the prop at 1/3 point. On the other hand, this beam can be designed for whatever the moment that is coming. But we have to be little careful here. I'll explain the reason. So if you are going with props, then only a smaller span of the beam is loaded. Otherwise, if you are not going to have props, the full length of the beam will get loaded. When the self-weight is not a major problem, the moment you place the beams, place the slabs, this will become loaded. And then we are going to place a concrete as well. So that's why I said it's good to have some supports at 1/3. So it's good to have some support at 1/3 point. Then how it's going to be? Then once this concrete has hardened, it is a structure like this. And we have to analyze it for the weight of the vehicles. We have to analyze it for the weight of the vehicles. So to analyze this for the weight of the vehicles, we use various theories. And one of the options available is to go for SAP 2000 analysis. SAP 2000 analysis by creating a grid of beams like this and apply the loads appropriately as given in whatever the code you have selected, and then find the bending moment. So what you have to understand is, when you cast it, very little stress. It's a no stress. When you place the beams, if you provide it without the supports in the middle, it can be subject to higher stress. On the other hand, you can keep it propped, keep the beam propped, So I'm talking about 6 to 8 meter long bridge beam that can be kept propped. And later, when the full composite action is available, then we can remove the props and allow the loads to come. So that is one of the options available. The other option available is, you do the casting without props, but then beam will need a lot of reinforcement for carrying the weight of the deck before the composite action is available. So when the bridge is hardened, all these are going to act as one unit because we are placing somewhere. So all these are going to act like one unit. So you can always apply the loads that will be transferred based on the vehicles and other. Right. So this is the situation. Now we see how we can model it for analysis. So we have to first decide how these roads are coming. What is the nature of the road? What is the nature of the road? And let's say we are going to have a 2-lane highway giving a width of meters, and then sidewalks 1.5 meters. Width of the sidewalks will be 1.5 meters. Now we have to develop a solution. What is the solution? So here we get 1.5 meters, and here you get 3.5 meters. Here you get 3.5 meters. Here you get 1.5 meters. So the next question is, how are you going to arrange the beams? How are you going to arrange the beams? So to arrange the beams, we can make use of one beam at the corner and the next beam somewhere here at a distance of 1.5 meters center to center. And then we can have 2 more beams. So up to here, we have to go for another 3.5 meters. And what can you say about the distance? So this will be about 1.75. So once you arrange the beams like this, and the last one, and you can cast the deck. And then place the place it, the bearing course, the concrete above, and you can have sometimes the bearing course about to prevent skidding. So that is page number 11. Now your task will be to find the bending moment. So for that, what we do is we draw a grid of beams. Like that. And then we fix at this location. And rest we can allow it to move and do whatever it wants. So to represent it in the other direction, we need large number of beams at smaller spacing, sufficient spacing. And then what we do is we are going to apply the load. So if they are at 1 meter interval, then we can apply a load of 5 kilonewtons per meter. Consider that these are at 1 meter. You can apply a load of 5 kilonewtons per meter over a width of 1.5. Now you have to simulate what is going on with this 9 kilonewtons per meter square load on a 3 meter area. 3 meter area. So over every 3 meter, you should get a load. But here you can see we are little away from that. So over a 3 meter lane, we have to get a load of 9 kilonewtons per meter squared. And I'm not very sure whether you can recall it. And I'll quickly go to the other file. Just one moment. Right. So when you look at the loads, you can see we can apply 9 kilonewtons per meter square load, and we have to consider this particular load that is acting, which is having a magnitude of 300 kilonewtons. 300 kilonewtons. So when you create a grillage, the advantage is now you have to see this load is acting over 9 but over a width of 3 meters. So up to this point, now you can apply 9 kilonewtons per meter line load. So you can apply it. But you have to see that you have to stop somewhere there. Then in the other lanes, now this still the lane is not over. So you have come up to these 1.5 meters, then you go for another 1.5 meters, and the remaining portion is 0.25 meters. So sometimes you will find that it's not a major problem. So you can actually apply 9 over the full width and just consider it as it is, right? So we'll apply 9 kilonewtons per meter over the full width, because those are the locations that the beams are coinciding. So when you apply all these loads on the transverse members, what will happen? You get a grillage, which is a frame of horizontal members subjected to vertical load. So basically, by looking at this, now what you do is you can create a grillage and apply the loads in a reasonable manner, and then run it, and then get the bending moment. And you have to get the most critical bending moment, right? So that's the procedure. And first thing is to create a grillage. And if I want, I can show you some of the simple grillages that we have created. So analyzing a bridge is not extremely complicated. Only thing is you have to look at, now this is a grillage for a beam, particular bridge beam. And once you create these loads, you can either apply it as a transverse load or a line load. But sometimes applying the loads on the transverse beams is preferred. And then once you apply the loads, you can get the bending moments. And when you know the bending moments, you can always find the reinforcement, because I have just explained how to find the reinforcement when the grade of concrete and the bending moment is known. So that is the procedure that we have to use. And I'll stop share. And then if you, yes, sorry, I'll share it. Right. So using these methods, so you can see from the village, you can get all the bending moments, shear forces, torsional moments. And then you can actually go for this particular arrangement of precast beams and precast slabs. And then because you can, the moment you apply the relay analysis, find the bending moments, then you can find the reinforcement. And I have already explained how to find the reinforcement. So this is the method. And again, to get a good start in this particular presentation, we have given the kind of reinforcement needed at each section. So a lot of information is given in this presentation, and we don't expect you to use these values, but this is a good starting point. You can have a look and see what are the values that you can use. So any questions on this? So when you have reinforced concrete structures like this, first thing is what we do is we optimize the structure, and then we have to analyze the structure, get bending moments and shear forces, and then we have to find the reinforcement needed in the beams and slabs. So that is the design method. To find the reinforcement in the beams and slabs, you can make use of the examples that we have just discussed. So in that one, I showed you how to find the reinforcement when the section is known. So any questions on this? So if you want to optimize a reinforced concrete structure, don't go for a slab bridge. If you just go for a slab, then you are losing a lot of concrete, because concrete is cracked in a slab bridge. And then in addition to it being cracked, it will add to the weight of the structure. So because of that reason, I told you that we prefer removing some part of the structure like this, removing it, and then so we like to So we like to remove part of the slab and come up with beam slab construction. And once you come up with beam slab construction, you have to see how to find the reinforcement after performing an analysis using SAP 2000 or any other software. So that is the real ground situation with respect to reinforced concrete bridges, and they are actually economical. They can be made out of high strength concrete. You can, if you can buy some admixture, then you can easily use admixture when you are doing the site based precasting operation. And so when it is flowing type concrete, you can easily pour it and get a good quality finish. And also when you go with the high strength concrete by using fly ash, what happens is these reactions will occur over a long period of time, and then you can end up with really tough section for concrete. And when you have a tough section for concrete, the steel will be properly protected, so you can easily hit 80 to 100 year or even more durability. So that is the position, and time is almost up. And if you have any correct any questions I can answer. How can you decide spacing of beams in both directions? So actually, when you are doing the grillage, we don't have actual beams in this other direction, but it's a good question. And that is, when you are doing the precasting operation, that is something I missed. It's a good question. So you have to consider what is the width of the slab, and this is going to be a 200 millimeter thick slab. And precast, what we precast can be about 90 to 100 millimeter. So if you cast this for a width of 150 millimeters, then we can optimize the reinforcement, because we can have this at 150 spacing, and here you can get 75. So when you place two slabs, the Jersey slabs, it nicely fits because we have some reinforcement, and then we have this, and the gap here is 150, and the gap here also 150. So when you go with the slab width of 450, you can actually get a spacing for the reinforcement of 150 millimeter. In a slab, it's usual to expect something like 12 millimeter bars. Sometimes when you do the calculations, you can find even 5 millimeter bars would be, or even 10 millimeter bars would be sufficient. So have I answered your question on how to decide on the spacing of beams? And other than that, there's no specific reason, but don't try to have a huge spacing for the precast beams, because we are going to place the precast panels on it. And what happens is, when you apply precast, when you keep the precast panels on the existing beam, we have to think about the weight of the panel if we don't have a crane. So these panels also could be heavy. We need about 4 people to handle a beam, sorry, a slab. So because we are talking about a 1.5 meter length and a thickness of about 90 millimeter or 80 millimeter, and then we are also talking about the length is 1.5, thickness is about 80, 90, and the width is 450. So it's if you look at the weight of this one with 1.5 meter spacings, 450 multiplied by 80, and that is 5 divided by 10 to the power 9. To the power 9. So that is then you have to multiply, sorry. So that is 1.5 into 0.45 into 0.08 into 25. So 1.35 kilonewtons or 135 kilograms. So this panel is going to be about 135 kilograms. So so you have to be a little careful. If you select a 2 meter spacing for the longitudinal beam, sometimes you will find that beams are also too much loaded. So because of that reason, general rule is we try to keep about 2 beams per lane. Altogether 3 beams supporting a lane. 3 beams supporting a lane. So because the lane width is 3 meters, so we can actually go for something like 1.5 meter spacing for all. and then once you do this, because we are loading with 3 meter span, 3 meter wide roads, so you can see even 1.5 meter uniform spacing also can work very well. So these are the kind of information you might like to share. And so if you look at a bridge, wide bridge, you might find that we can go for multiples of 1.5, 1.5, 1.5, 1.5, and here you get center of this is 3.75. So you can repeat this side with this side, and then you can get a solution. So always keep in mind, we are precasting, so the lifting operation is important. If you have a crane, no problem, no restriction. But if you don't have a crane, people will have to handle this. So you have to be little careful. Even during precasting, they have to handle it. So don't make them too big, not too wide, not too long, because we have to make sure there are adequate number of structural beams to transfer the loads onto the two supporting members, maybe two abutments or abutment of pier. So because of this reason, we generally like to see a spacing of about 1.5 meters maximum. Is that clear?
Yes, sir.
Right. So with that, shall I conclude? So today
yes,
I took little time because there may be some who are not very familiar with Eurocode. So that's why I explained how to calculate the reinforcement. Because without knowing how to calculate the reinforcement for Eurocode, you cannot actually do a design complying with Eurocode. So once you learn how to calculate the reinforcement quantity as for Eurocode, you can easily design a reinforced concrete beam slab bridge. Is that clear?
yes, sir.
Right. So next week onwards, we'll move on to other types of bridges, and somebody has requested structural analysis as well. So either next week or following week, I will produce a village and then show you how to find the bending moments, shear forces, and torsional moments as well. Okay?
Okay, sir.
Right. Okay. Thank
I
you.
would like to
Yeah.
invite Engineer Joga Prajapan to deliver the vote of thanks.
Good evening, participants. It's great pleasure to propose the vote of thanks for this valuable session with topic of designing cost-effective and durable reinforced concrete bridges as for Eurocodes. I would like to express our gratitude for our distinguished presenter, Professor Tishan Jayasinghe, Senior Professor, Civil Engineer Department, University of Moratuwa, for your informative lecture, sir. Then I wish to thank Engineer Kamala Gunawardana for your support as President of Civil Sectional Committee. And in addition, I extend my thanks to Engineer Banduka and Technical Events Subcommittee and IT and technical officials of Institute of Engineers Sri Lanka for organizing this lecture. Thank you. Thank you for all the participants.
Yeah, thank you very much. Thank you.
Thank you, Professor.
Thank you. Thank you.
Vote.
Thank you.
And
Thank you,
sir,
Bandhuka and Yoga Pro.
Yeah.
Thank you, sir.
sir, there's a
Yeah. Thank you.
Sir, there's a
Yeah.
request to share the handwritten pages. Is it possible?
Handwritten pages, I think I might have to take a photo and share it with you.
And actually, it is on the recorded video as well.
Yeah, recorded
someone
video
has
has captured most of it, but we can actually, I can take a photo and send it. Shall I do it tomorrow?
Oh, that's fine, sir. Thank you
Yeah,
very
no
much.
hurry.
Right. Okay.
Okay.
Okay,
Thank you very
then.
much, everyone.
Thank you, everyone.
Thank you, sir.
Thank you. Thank you.